Good morning. I'm very glad to be here today to present my work. My name is Sabrina. I'm a PhD candidate at McGill University. Today, my lightning talk is about parent-child math attitude on home numeracy practices, a perspective on Canadian children. The concept of home numeracy is getting increased attention since last decade. Literature mostly gave focus on the numeracy aspects of home math environment. So here, that's why we use the term home numeracy environment instead of home math environment. In particular, there is a wide research support on the role of home numeracy environment. Home numeracy environment defines and explains numeracy activities of children and their family, particularly parents' involvement in those activities. As children's foremost educator, parents often influence the home numeracy environment. From the previous research, we got to know that there are two specific components of home numeracy environment. One is explicit components, another one is implicit components. Explicit components are the components which are directly observable. For example, the home numeracy practices. If we see that a child is playing math apps, a child is counting apples, so these all are the parts of the explicit components. Whereas implicit components are the underlying factors which serve for the explicit components of the home numeracy environment. For the implicit components, math attitude is one of the most significant or vital factors which serves as the underlying factors of this component. So for the math attitude, as I already mentioned, children and parents, both of them are involved in the home numeracy practices. So parents' math attitude and children's math attitude both matters. Math attitude, in our study, we use the term math attitude by combining several features, for example, such as math motivation, math self-efficacy, and math anxiety. So the explicit and implicit components, both components contribute to children's math development. And as I already said, parental and child math attitude together serve as the implicit components of the home numeracy environment that may directly or indirectly influence the explicit aspect of the home numeracy environment. However, there is a still dearth of research on whether parent-child math attitude predict the home numeracy practices, which is an explicit component of the home numeracy environment. Specifically, we need to know to what extent there is direct and indirect effects of parents' math attitude on home numeracy practices. Considering this, the current study investigated the extent of home numeracy practice experienced by Canadian children and whether child math attitude and parents' math attitude have an effect on home numeracy practices. 3 research questions guided the current study. First one is what are the home numeracy practices experienced by Canadian elementary school children? Second one, do home numeracy practices differ based on gender and grade levels? The third one, does child math attitude mediate the relations, if any, of parent math attitude on home numeracy practices? To conduct this study, children from grade 1 to grade 5 and their parents from a Quebec school were participated. We had total 117 parents and 117 children. To conduct this study, first we got the consent form from the school boards, from the schools, and then we got the consent from the teachers and parents. We sent out the parental measures to home so that parents can fill it out, and the children they filled up the measures at school. So we used 2 types of measurement tools for our current study. One was the math attitude measures, other one was home numeracy practice measures. Math attitude measures were administered by both parents and children. For parent math attitudes, we used 3 kinds of skills: math motivation skill, abbreviated math anxiety skill, and math self-efficacy belief skill. All skill were 5-point Likert type skill. For the children math measures, attitude measures, we used the similar kind of skill, except for the math anxiety skill, we used the skill which were developed for the children, specifically designed for the children. For home numeracy practice measure, we used a parent questionnaire, which were developed asking 5 domains of home numeracy practice. arithmetic, academic learning, numeracy, and time shape and spatial manipulation activities. Like the math attitude measures, the home numeracy practice measures were 5-point Likert type skills from which was like 1 was never to 5 was always. So that were the measurement tools for this study. And then we did the preliminary analysis. So in response to the research question 1, the preliminary analysis showed that the participants varied in the frequency of home numeracy practice. On average, the most frequently occurring home numeracy practice was arithmetic activities, whereas the least frequently occurring was time, shape, and spatial manipulation activities. In response to the question 2, independent sample t-tests showed that there were no gender differences on home numeracy practices. Regarding the child's grade level, one way ANOVA showed that there were no significant group differences in arithmetic, academic learning, numeracy, and time, shape, and spatial manipulation activities. And then we did the postdoc analysis. The postdoc analysis showed that grade 1 and grade 4 children do significantly more academic learning activities at home than grade 5 children. Again, grade 1 children do significantly more numeracy activities at home than grade 4 and 5 children. For the third question, we saw that parents' math self-efficacy only predicted child math self-efficacy, but not home numeracy practice. For the parent math anxiety, the results showed that parent math anxiety didn't have any effect, neither on children's math anxiety nor home numeracy practices. On the contrary, we saw that parent math motivation predicted both child math motivation and home numeracy practices. So the outcome of the result gave a significant contribution, and the current study adds a valuable insight to the limited literature available on the role that parents' math motivation has on their children's math experiences at home. It seems parents' motivation to provide a quality home numeracy practice for their children may win out over the self-doubt and worry they personally experience from math. Thanks for being here today. Thanks for listening to me. If you have any questions, you can ask me, or if you have any interest to know about my research, you can email me. Thank you so much. Does anyone have any question? Or we can go to the next presentation.
I'll ask a question. Great work. Very interesting findings. I guess I'm wondering about, why do you think that the finding that first grade children engage in more home math activities in 4th and 5th? Is it perhaps the fact that 4th and 5th graders maybe have more math in school, and thus maybe parents don't feel the need to do it as much as home? I'm just wondering about that finding.
Actually, the results show that. I think we need to have a more deeper investigation about it, like what's the reason behind it, because we also don't know what's the reason behind it. But it was really intriguing, like depending on the grade, maybe depending on the grade, parents' involvement, it becomes more intense or they become less involved with the kids. So yeah.
Okay, thank you, everyone. Sorry that there was a time lag in my screen, so I wasn't able to see you for like 10 seconds. So thank you for the time now. I'm Eason from the University of Hong Kong. So today I'm going to share with you a study about the relation between relational reasoning and arithmetic computation. In particular, we want to explore the mediating role of complement understanding, which is an important arithmetic principle. So let's start with the definition of relational reasoning. It is an ability to derive meaningful patterns behind some information that may seem unrelated. And previous research has shown the close relation to mathematics learning. But relational reasoning is not a unitary construct. In fact, there exist different forms of relational reasoning because there exists many relations among concepts or schematas. So in our study, we adopted a four-form framework. So for the sake of simplicity, I will refer to RRABCD, which can be defined by their keywords, which are similarity, deviation, incompatibility, and opposition. And these relations are suggested to be very important for mathematics learning. So now we know that relational reasoning is important and can contribute to mathematics, but what is the underlying mechanism? So in our study, we propose that it may be through the understanding of complement principle. So what is complement principle? So here is a classic example of this principle. It is suggested in the literature that understanding of this principle would facilitate the use of working backward strategy, as well as allows deep understanding of part-whole relations. And in some previous studies, it has shown that understanding of complement principle would predict future arithmetic achievements. So for the linkage between relational reasoning and complement understanding, so here are some proposed linkages, but for the sake of time, I will not go into details about it. So in short, the reasoning skills about different relations can contribute to the acquisition of this important arithmetic principle. So given the above background, we come to the hypothesis that each of the mentioned four forms of relational reasoning would have unique contribution to the students' arithmetic computation performance. In particular, the relation would be mediated by complement understanding. So here comes the method. A little bit about the background. The current study is actually a part of the longitudinal project on arithmetic principle understanding. So data from 3 time points were used in this study. There are 240 data points, which are all 5th graders. So here are a glimpse of some of the measures used in the study. Here are the sample items of the relational reasoning measure, as well as the complement understanding measure. Given the multifaceted nature of arithmetic principle, we used 3 different measures to tap the understanding of this arithmetic principles. So in conclusion, we propose a model like this. In short, the 4 forms of relational reasoning will predict the understanding of complement and in turn affects the performance in arithmetic computation with the control variables here. So here comes the results. First, we check the model fit. It's shown that by the fit indexes that the model fits to the data very well. And the model shows that among the 4 forms of relational reasoning, reasoning about similarity, deviation, and incompatibility would predict understanding of complement principle and in turn affect students' arithmetic computation 6 months later, but not the reasoning about oppositional patterns. So here comes the discussion part. So this slide mainly summarize what I just talked about in the model. And then for the implication, I'll highlight some important theoretical and also practical implications. For theoretical one, it is the first study to investigate unique contribution of each form of relational reasoning, as well as the first study to explore the underlying mechanism, which is the understanding of complement principle. And for the practical one, it would be interesting that because the findings in the current study points to the need for an intervention, a new intervention for mathematics learning in elementary level. In particular, it would be very useful for children with mathematics anxiety because intervention on relational reasoning skills would not involve any numbers that will provoke anxiety. Finally, there are some limitations and future directions. For example, the choice of control variables may be changed in future studies. And the current study may also be replicated with at least one more time point to clarify the direction from relational reasoning to complement understanding. Lastly, the experimental design will be needed to confirm the causality. So thank you all for your attention. Feel free to ask me any questions. And if you have any further questions, feel free to send me an email about that.
I have a question. I don't know who's moderating, but can I ask a question?
Sure.
Yeah, so I'd like to know what's a little bit more about the one form of relational reasoning that did not predict the complement understanding. So is there something more distinctive about that particular form than the others? The slide that showed the different types was very quick, and so it was a little hard to get a handle on what it is about the ones that did predict and what was different about the one that did not.
Yeah, thank you for your question, Martha. I will stop here at this slide to let you read a little bit more about the items. It is actually quite surprising for me as well, because I think in nature, complement principle is kind of oppositional or compensatory in nature. But then for RRD, which is antithetical reasoning, which requires participants to find out the oppositional process in among these four choices. So at first, before the actual study, my hypothesis is that RRD would be the most predictive one, but then in turn, it turns out to be the only one that is not predictive of the future arithmetic computation. My speculation would be that the oppositional process involved in this reasoning process may be very fundamental, that because our sample now is the 5th graders, which may be already quite advanced. So they may have acquired a certain level of complement understanding. That's why the current predictions may not stand for the participant at this age. Yeah, so yeah. I was now. Yeah, hope this helps you. So yes. I'll give the floor to next presenter.
Sorry, took me a second to find the unmute button there. Hi, I'm Rachel Conlon from Florida State University, and I'm going to talk about our work examining the relations between math gender stereotyping and the gender stereotypicality of career aspirations in children. So by early elementary school, children are already aware of what abilities and which careers are stereotyped to which gender, and they even show gender stereotyped career aspirations themselves. And this is influenced by what they see around them. So the truth is that many careers in the US are largely gender segregated. The vast majority of nurses are women, for example. The vast majority of engineers are men. And so this might lead kids to infer that these imbalances in these careers are because of these purported differences in abilities. And then their own perceptions of their abilities might influence what careers they think they can do. And because we're a lab that's interested in math, we wondered how math gender stereotypes specifically, so stereotypes that say that boys have more natural sort of affinity for and ability for math, relate to children's career aspirations. So we asked a few questions. So first of all, we wanted to see if boys and girls see gender stereotyping in the same way, and if their gender stereotype levels are different. Then we wanted to know if the proportion of children aspiring to gender stereotypical careers was different between girls and boys. And then lastly, we wanted to know if we could use kids' math gender stereotyping to predict the kind of career that they might aspire to in the future. So for a sample, we had 520 third grade students who came from a larger longitudinal study about teacher math anxiety and student math outcomes. And we first asked them what job they wanted to have when they grew up. We then classified these jobs so that if more than 75% of workers in the US Census were the same gender as the child for that job, it was considered gender stereotypical. If more than 75% were a different gender than the child, it was considered gender atypical, and everything else in between fell into kind of a gender neutral category. Then to address stereotype awareness, we asked them how good they thought most people thought men and women were at math. And then we had two measures of stereotype endorsement. So we looked at how good they thought boys and girls were at math and men and women were at math. And they answered it on a 4-point Likert scale. We then took the scores about women and girls and subtracted them from the scores about men and women. And so this gave us a gender stereotyping score where if they had a 0, it indicated sort of neutral views, negative numbers indicated female biased views, and positive numbers indicated male biased views. And what we found was that boys and girls did show differences in their stereotyping. So for all 3 stereotyping measures, we found a significant difference between girls and boys. What we see here is that girls had these female biased stereotypes and boys had these male biased stereotypes, with the exception of stereotype awareness. So that's the how good do you think most people think men and women are, where boys actually didn't show stereotyping that significantly differed from 0. So we also found that the proportion of students aspiring to gender stereotypical careers differed by gender. So almost 40% of girls chose a gender stereotypical career versus about 20% of boys. And then lastly, we tried to predict gender stereotypical career choices from math gender stereotyping, and we couldn't do it. So the only significant predictor in our model of choosing a gender stereotyped career over an atypical one was gender, as we might have expected from our results from the second question. So what does this tell us? So we're seeing this own gender bias in views on math ability rather than what you might truly call stereotyping. And this is somewhat consistent with research that says that younger children have a tendency to think that their own gender is just generally better at everything. And it may be that these kids are just a little bit too young to show the kind of stereotypes that we see in older kids. And we did find that more girls chose gender stereotypical careers, which may be problematic, but stereotyping scores are not going to be helpful in predicting those choices. So we need to look forward to see, well, what might be helpful? So it may be that we need to move to looking at older students or these same students when they're older to see if stereotypes are predictive at that point. It may be that other stereotypes are important, like reading ability stereotypes. But it's also important that we look at other contributors to particularly girls' career choices and maybe their choices not to choose a gender atypical career. So it could be that they don't have a sense of belonging in those careers, or maybe that we're not fostering enough interest in them. So that is everything. Just wanted to thank my lab and IES for funding this research. Could take any questions. Oh, I think I see Marta's hand up.
This is very interesting work. Thank you. That was great. I guess I was wondering, and I don't know if you did this analysis or if it's maybe just a little bit more like your sort of anecdotal instinct, but what proportion of the careers had anything to do with math for both genders, right? Like, why would we expect math stereotype to predict if they're careers that are like, you know, I want to be an artist or, you know, some sort of careers?
About, I'm trying to think, with a larger sample of the same age group, we had about between like 14 and 20%, depending on what you consider to be like a STEM career. But the careers that were gender stereotypes, so a lot of stuff fell into the neutral. The ones that particularly fell into male stereotypes, with the exception of like construction and policing were primarily sort of science and math type careers, which is sort of why it's also the measure that we had, but it's sort of why we thought that it might, that they're very gendered, and the STEM kind of subjects seem to be where that gendered career things fall. Okay, I'm going to stop sharing so that Jeff can speak, but if you have any questions, feel free to email me.
Thank you, Rachel. So Jeffrey, when you're ready.
All right, thank you, everyone. Hi, I'm here to talk to you about composite numbers. This is work in collaboration with Rena Harsh and Shashank Varma. So we're interested in composite numbers in part because it's interesting that some numbers are more composite than others. And what we mean by that is, for example, you take a number like 72, it has a factor pair of 2 and 36, but it also has a factor pair of 3 and 24, and 3 other factor pairs. So this is what we would call a highly composite number. And its near neighbor on the number line of 72 has only 3 factor pairs. But its other near neighbor on the number line of composites is 74, and that only has 1 factor pair. So we see that different composites have different amounts of factor pairs, but also it's not a regular relationship with the size of the composite number itself. So if we're trying to retrieve a factor for a composite, for example, retrieve the factor 8 for 72, perhaps there's actually some interference from the fact that this is a densely populated neighborhood of factors. And if we take a look at the range of composite numbers from 4 to 100, here we see on the x-axis the composite numbers, and on the y, the number of unique factors. We see that this is not a regular relationship. There's quite a lot of variability in the amount of factors for each composite. But importantly, many of these factors are actually well practiced as part of the 12 by 12 multiplication table. And so if we're trying to retrieve a factor of 8, for example, from 72, the question is, how could we look at this? Well, in prior research, most of this has been done in multiplication tasks. So in arithmetic production, answer 8 times 9 or 9 times 8. And work has suggested that this produces activation of the multiplication table for multiples of 8, multiples of 9, leading to the highest activation for 72. But there's also activation of near neighbors on the table of products, which might lead you to a confusion error. For example, saying 8 times 9 is 63. We aren't interested in that task because that gives you both of the factors. So we want to go the other direction. So instead of doing an arithmetic production task, we're going to hide one of the factors from you in an algebraic task and have people try to produce what the factor is. So in x times 9 equals 72, what's the factor that goes where x is? What does x represent? So we wanted to look at this task as well as a novel task that asks just, is 8 a factor of 72? Yes or no? Or the other direction for 72 is 8 a factor. So we call this a factoring verification task. So our questions are, does the size of the neighborhood, does the amount of unique factors for a composite interfere with factor retrieval? In other words, is it going to be harder to retrieve factors if the composite has more unique factor pairs for like 72 compared to 70 or 74? Additionally, is this moderated by practice effects from the 12 by 12 multiplication table? And finally, do we see the same pattern for the 2 different tasks? So we have these 2 novel tasks, algebraic production and factoring verification. Do they lead to similar results? So to do this, we recruited 48 undergraduate participants, and we had them complete these tasks. Both tasks, the algebraic task and the factoring task, were counterbalanced for order. And there's a total of 74 unique problems per task for the 74 composite numbers. So in the algebraic task, each participant receives a random single-digit factor question. And for the factoring task, they receive just a random factor for each of the composite numbers. And our dependent measure here is basically what's the mean log RT to adjust for skew for each unique fact for correct trials only that are answered in less than 10 seconds. And so here, let's take a look at the results for the algebraic production task. So again, that's at like x times 9 equals 72. Here we'll see for the non-table facts, those that aren't on that multiplication table, what is the relationship between compositeness on the x-axis, where the more unique factors, the farther to the right, and the response time, log RT, on the y-axis. And here we see for the non-table facts, there's no relationship between how composite a number is and how long it takes people to respond to this algebraic task. But for the table facts, we see the predicted significant positive relationship. In other words, the more composite the number, the more factor pairs there are for that number, the longer it takes to retrieve a factor, but only for these practice table facts. And this relationship was significant even after controlling for the size of the product or the composite number, as well as the factor itself. What about the factoring verification task? Here we see the same pattern. There's no relationship for the non-table facts, but for the table facts, we again see significant interference effect for answering this question of is 8 a factor of 72? And we see this pattern actually across both phrasings of this factoring verification task. So in conclusion, for both of these tasks, we get a significant interaction between compositeness and whether it's a table fact, such that for table facts, you're actually slower to retrieve factors if the number is more composite, but we don't see this relationship for non-table facts. And this is true even after controlling for the composite number size and factor. So we think this is evidence for more interference from the larger factor neighborhoods when they're well practiced. So for a practiced fact like 8 times 9 from 72, we're getting interference from these other factor pairs. And that's less true for a number like 70 or for 74. Thank you to these people, and I'm happy to answer any questions. Yes, Martha.
Hi, that was super interesting. My question has to do with whether you could capitalize on variability in the tables that people learn to make different predictions about how interference might differ for different participants. Many kids in the US only learn the table facts up to 10, not up to 12. And so that might make different predictions about whether certain interference occur and certain ones don't. Also, kids in different kinds of math curricula experiences have different degrees of practice with the tables. And so it seems that what you're showing should also relate to how well practiced those facts are. And so you might see, for example, that kids who have a traditional curriculum that has lots of drill and practice might show lots of interference, more so than kids who have more concept-based curricula that aren't as heavy on drill and practice. So, yeah.
Yeah, those are wonderful questions. I wish we had that data, but those are great suggestions for future. I'd love to look at that. Thank you, Martha. I agree with your predictions. Okay, I think whoever's next.
Okay, it seems that So Young could not make it today. So Martha, when you're ready.
Oh, sorry, it looks like I have to restart from the beginning. Okay, cool. Can everyone see things that they should see? Wonderful. Hi, everyone. I'm Marta Mielicki. And together with Charles Fitzsimmons and Clarissa Thompson, we were looking at teachers' attitudes towards fractions. So our primary research question here was whether teachers reported more negative attitudes towards fractions relative to other number types, and also whether teachers reported higher levels of anxiety related to fractions, specifically relative to other math content. So we know from prior work that children and adults tend to report more negative attitudes towards fractions relative to whole numbers, and actually towards other numbers like percentages. And we also know that fractions are notoriously difficult content for learners, and also extremely important and predictive of later math achievement. And so there's some evidence to suggest that teachers' attitudes and anxiety may impact students, although some folks on this call, including Rachel Conlon, have actually not found that effect as far as teacher math anxiety not impacting student math anxiety. But there is some other works that kind of suggest that the adults in children's lives and their attitudes and anxiety towards math can have these impacts on children and learners. So we had a sample of teachers and compared them to a sample of MTurk adults from the original study by Sydney et al. And so importantly, all of these teachers had experience teaching fraction content. And most of the sample reported over 5 years of teaching experience. So this was a relatively experienced sample, and all of them taught fraction content. So we administered the math attitudes questionnaire, and this scale has items pertaining to self-perceived ability, which I've showed you here, but there's also a scale for preference, frequency of use, and perceived importance. And so we average across all of these scales to get these indices of math attitudes. And we also administered general math anxiety, so a 1-item scale of 1 to 10, how math anxious are you? So both the teachers and the MTurk adults saw this item. And then the teacher sample also responded to a fraction anxiety in the same form, except instead of how math anxious, it was how anxious about fractions are you? So we'll just orient you to this graph. So I'm going to show you, so this is specifically for the math attitude. So on a scale of 0 to 6, with 6 being more positive, closer to 0 being more negative. Math attitudes. And so I'll show you the teachers and the MTurk adults and comparing attitudes towards whole numbers versus fractions. So do teachers report more negative attitudes for fractions than whole numbers? Yes, we did see a large effect with teachers reporting more negative attitudes towards fractions relative to whole numbers. But how does this compare to the sample of MTurk adults? So there was actually a smaller disparity for teachers between their attitudes towards the number types as far as the difference between these bars relative to the MTurk adults. And also the teachers had more positive attitudes towards both whole numbers and fractions relative to the MTurk adults. So next I'll show you the math anxiety findings. So same idea, except now we're looking at math anxiety here on the y-axis, and this was out of 10. With higher numbers indicating higher math anxiety. And so do teachers report higher anxiety for fractions relative to other math content? And the answer is yes. Here we see a medium effect, but again, how does this compare to adults kind of more generally? And so recall that for the MTurk adults, they only received the general math anxiety measure and not the fraction specific. And we did see that teachers actually reported lower general math anxiety than MTurk adults. So some bad news, even experienced teachers have more negative attitudes towards fractions relative to whole numbers. And even these experienced math teachers report higher anxiety about fractions relative to other math content. But there's also some good news, which is that teachers seem to have more positive general attitudes towards both number types, fractions and whole numbers, as well as lower math anxiety than a sample of adults. And so this work is important because teacher attitudes might impact student attitudes. And if teachers impact negative anxiety or negative attitudes and anxiety towards fractions, this could contribute to learners' attitudes and anxiety, which could perhaps impact learning outcomes down the line. Any questions? And also here's my email if you have further questions.
Okay, I think I'll call on the next presenter, and maybe we could open for questions again at the end of the symposium today. So the next one, it's going to be Miso Kim.
Alrighty, everyone, I'm going to go ahead and share my screen. Is everyone able to see this? Perfect. Okay. Hi, everyone. My name is Miso Kim. I'm a senior here at Elon University, located in North Carolina, and my undergraduate research study is on Korean American parents and how they support early childhood numeracy. So to begin, I thought I would share some theoretical frameworks that we use to support our research study, and beginning with Vygotsky's sociocultural theory, which I'm sure many are very familiar with, but to highlight this theory emphasizes how parent-child interactions are actually very critical for children's learning. And another relationship that I found while delving further into literature and what's out there in the field is a relationship between young children who are introduced to math principles at an earlier age. They're more likely to have later academic achievement and success later on. And the gap in the research that we hope to address in this study is, despite there being an increased amount of research on home numeracy environment and in cultural, like specific cultural contexts, there is very little research on the specific population of Korean American families. As for the research questions, there's two primary questions our study hopes to address. The first being, how do these parents support early numeracy? Specifically, what kinds of activities these parents report in engaging in with their children, and also how Korean American parents, what their beliefs are about the importance of math in the home environment, and also what their own home numeracy environment or HNE experiences were like growing up. For the methodology, it's still an ongoing study. I've been working on data collection and still getting some participants. As of right now, I have the survey component as well as the follow-up interviews, and I have 15 Korean parents who have children between the ages of 3 to 5. And the survey items were compiled based on prior research and different skills together that address formal and informal math and literacy activities, parent beliefs, and the specific parent-child interactions they report engaging in. And these parents were contacted through community newsletters in North Carolina, as well as snowball sampling. To begin, I just wanted to highlight some survey findings that I've found so far. These parents reported engaging in counting objects. As you can see on the graph, roughly 64% of parents have reported that these children count objects daily, which is interesting, as well as numbers, more informal activities such as puzzles, baking, calendar activities like correlating the number associated with the month, board games, and also online games as well, with the increase in technology these days. And as you can see on the graph, it slowly starts to dwindle. Besides the children counting objects and counting daily, you can see that there's more focus on informal activities such as math games and number activity books. And if you look down at the very bottom, roughly 14% of parents reported that math flashcards were used daily. So that's a more formal approach of integrating math principles into children's learning on a day-to-day basis. And also approximately 77% of parents agreed that math is important to implement in daily living. And also 57% of parents indicated that they were more comfortable teaching literacy, even though they did indicate that both math and literacy are supported in the home. Alrighty, and then as for the follow-up interview, it was just a follow-up interview to elaborate further on the different activities and what these parent-child interactions look like, because obviously the survey can be quite limited in terms of what kinds of responses we can collect. But one relationship that I thought was important to highlight was the pandemic component that our survey and study hopes to address as a whole. And the parents did indicate that they noticed their children in math and literacy levels to increase during the pandemic. Some of the follow-up interviews, the parents indicated that they've switched gears to a homeschooling curriculum just because they prefer their children not to engage in virtual ways of learning. And because of this lockdown, there was an increase and influx in parent-child interactions overall. And one quote that from the follow-up interview I thought really encapsulated this relationship that we've been finding so far is a parent indicated, we're able to give her the child one-on-one attention and challenge her as she goes. And we're a bit more enlightened about our kids because we do spend so much time with them during COVID. And once again, I just wanted to highlight that this is still an ongoing study, so it's a little bit early to have some conclusive results and discussion further, but I'm hoping to find a bit more on what I can address in the Korean American community and related to numeracy. And I just want to say this concludes my presentation. Thank you so much for taking the time to listen to me. And also, once again, to my research mentor who is also on this call, Dr. Marine Vandermaas-Peeler, the Elon College Fellows Program, who also has given me the opportunity to conduct this research, and also to the Math Cognition Learning Society. And if you have any further questions, feel free to email me at the address below.
Thank you. I think maybe we can open questions for Miso and then go back to Marta after, because we got a question in the chat.
Could I just ask a quick question? Yeah, just wondering, Miso, if you considered the language backgrounds of the Korean parents, because Koreans are more easier language in theory in some research because of the base 10 system. Have you seen whether they're teaching children with the base 10 in the Korean language and then?
Yeah, so that's actually something that we're considering while conducting this research. A component of the survey that we do ask is whether these parents are first generation, second, like the generational differences for whether they're Korean or Korean Americans. And also with that in the follow-up interviews, we do like to ask them, because with the Korean language, the numbering system is based on base of tens. And it really depends per family whether they like to emphasize Korean being the primary language spoken in the home. So that may also correlate with the style of learning and also the number system that they like to emphasize. So we're hoping to find a relationship between that as well.
Thank you. I think I'll go back to Marta. We had a question from Colleen.
Sure. Hi, Colleen, and congrats on the newborn, and kudos for like even being here with a newborn in tow. That's very impressive. So yeah, I think this is interesting. And I think, if I'm not mistaken, the research on suggesting that math teachers have higher math anxiety was with pre-service teachers. And so these teachers did have, over 5 years of experience and experience teaching fraction content. So it's possible, I think it would be an interesting comparison to look at pre-service teachers versus experienced teachers versus sort of MTurk adults or adults not engaged in teaching. So yeah, I think that's kind of what's driving the pattern here.
Thank you. I think I'll call the next speaker, Marissa Brown, and maybe if people have questions, they can keep on asking while she's setting up, or maybe type in the chat. Thank you.
All right. Hi, everyone. My name is Marissa Brown, and I am the project coordinator in the Development and Learning Lab at the University of Dayton under the direction of Dr. Mary Foos. And this is a pre-registration of an experiment to test the malleability of young children's flexible attention to numerical and spatial magnitudes. So a little bit of a background. Children often have trouble disentangling conflicting dimensions of magnitude, which is likely due to a lack of experience with incongruent numerical and spatial magnitudes. And previous correlational studies have shown that children's ability to flexibly shift focus between numerical and spatial magnitude dimensions, which we have termed flexible attention to magnitudes, or FAM, is predictive of growth in math achievement in preschool beyond other known predictors of early math skills. So this is the third experiment in a 3-experiment study, and this part aims to examine the causality of this relation using a FAM training intervention to test if it improves children's FAM ability and math achievement more so than classic counting and comparison activities or non-math activities. So for our methods, our participants will be children ages 3 to 5 with a sample size of 116, recruited from preschools in a demographically and socioeconomically diverse city in the Midwest. Children will be given a pretest, which will consist of the novel FAM task, which integrates executive functioning and early math skills, and where children are asked to make judgments, magnitude judgments, in cases where numerical and spatial magnitudes are incongruent, followed by the number sense subtest of the Woodcock-Johnson 4 tests of early cognitive achievement and development. And then children will be randomly assigned to one of 4 conditions, 2 of them being experimental. So those 2, one being size to number FAM condition, which will consist of incongruent stimuli, and children will be presented with first a set of trials where they're asked to determine which side has bigger animals, and then followed with a set of trials where they'll be asked to determine which side has more animals. And then also the mixed fam condition, which will include the size and number trials, but they will be intermixed. And then 2 control conditions. So a traditional congruent comparison control condition where the stimuli will be congruent, and then children will be asked to make judgments on magnitude. And then a non-numerical control condition where children will be presented with stimuli where they will not be asked to make numerical judgments, but instead be asked questions such as to name a shape or a color or something like that. And these will be in 8 20-minute intervention sessions with an experimenter, and then will be followed up with a post-test, which will again include the FAM task and the number sense subtest. For our statistical analysis approach, the data will be analyzed using an ANCOVA with the 4 conditions as the between subjects variable and covariates, including pretest scores, age, gender, and family income. And the results are expected to show that the experimental conditions will produce higher FAM and math achievement post-test scores compared to the control conditions. So thank you. This research is funded by the National Institutes of Health. I guess I'll take any questions now. Yes.
Maybe Renee has a question.
Hi, yeah, I do have a question. So are you using any kind of measure of mathematical language? I noticed that you said, bigger, and I think you said more. This is just an area I'm super interested in, is in this very early age, what we know about children's understanding of those key terms.
So right now we're only using the FAM task and the number sense subtest as a measure of general math achievement. We don't have a measure specifically for math language, but I do know that that's an important aspect of children's math learning. So that's interesting.
Yeah, I think what I was getting at is, can we know for sure that they were understanding the meaning behind what you're asking, which is bigger and which is more? Or whatever terms that you choose to use for those.
We do use the terms bigger and more, and that's an interesting point, that they might not necessarily know the meanings of those words, but we do use the number sense subtest, which has some questions that involve those terms that would maybe help us determine in the pretest versus post-test whether they understand those words, I suppose. But we don't have a specific measure for the math language.
David Purpura et al. Have I think it's undergoing some psychometric testing now. I used it for a study, but they've got an early language vocabulary assessment. You might contact him to see if you can use that. I don't know that it'll give you the data, because I don't really know the content and internal validity and reliability on it, but at least it might give you some information of, hey, they really had no idea what these terms even meant. So
yeah, that's a great suggestion. Thank you for that.
Thank you. I think these were all the talks for today. I hope I'm not forgetting anyone.